Hey everyone, and welcome to The Explainer. Today we're diving into a serious showdown, a real clash of the elements. We're on a mission to crown the most powerfut metals in chemistry by building the ultimate league table, the Reactivity series. First, just look at this. This is the death mask of King Tut. It was underground for more than 3,000 years. But that gold? It looks like it was polished yesterday. No tarnish, no rust, no change at all. It's practically immortal. So why is that? And that really gets to the heart of the mystery, doesn't it? How can gold look perfect for millennia when something we see every day, like an iron gate or a bike chain, can completely crumble into rust in just a couple of years? What makes one metal so tough and another, well, not so much? To crack this case, we have to think like chemical detectives. Our job is to build that definitive league table for metals, ranking them from the most chemically powerful, or reactive, all the way down to the least. And we're not just going to pull it out of thin air, we're going to use hard evidence from experiments to see who really comes out on top. So first up, let's quickly uncover gold's secret to eternal youth. It really all boils down to one single property. It's reactivity. Or, in gold's case, its lack of reactivity. All right, enough talk. Let's start building this thing. The Metal League Table. The competition starts right now. And for round one, it's the water test. We're going to see how our metals handle a little dip in some cold water. And for the tougher ones, a blast of hot steam. Okay, I know this diagram looks a little busy, but don't worry. The key thing to see here is how we test the really stubborn metals. A simple bath in cold water won't cut it. So we use this setup to heat up some wet glass wool, which creates a jet of steam that flows right over the metal. It's a much more intense, high-energy test. And here we go. The results are in. And wow, what a difference. You've got potassium, which goes absolutely bonkers in cold water. So crazy, in fact, that we're not even going to try it with steam. Too dangerous. Then you have magnesium, which is kind of lazy in cold water, but give it some steam and it puts on a brilliant, bright show. Iron won't do a thing unless you get it red hot. And then there's copper. It just sits there, doesn't care about cold water, doesn't care about steam, nothing. So right away, from just that one test, we can start to sketch out our league table. Potassium is clearly our top-tier champion. No contest. Magnesium and iron are hanging out in the middle tier. And holding up the bottom, totally unbothered, is copper. Our first draft is complete. Now, that water test gave us a pretty good idea. But to really settle the rankings, we need some proper head-to-head battles. So welcome to round two, the displacement duel. So, what on earth is a displacement reaction? Well, you can think of it like this. A more reactive metal is basically the stronger competitor. When it's put into a solution containing a salt of a less reactive metal, it literally proves its strength by kicking that weaker metal out and taking its place. It's pure chemical muscle flexing. And you can see it happen right here. It's amazing. On the left, you have that nice blue copper sulfate solution. Then we drop in some iron filings. Now look to the right. The solution has turned green. That's the new iron sulfate. And that reddish-brown stuff coating the filings, that's the copper that just got kicked out. We just saw, with our own eyes, iron proving it's more reactive than copper. And that little experiment perfectly demonstrates the unbreakable rule of this duel. A more reactive metal can always displace a less reactive metal from its salt solution. This rule is the secret weapon for finalizing our league table. And so, after all the water tests and all the displacement duels, we have it. The final, undisputed champions list. The Reactivity series. From the wildly explosive potassium at the very top, down through the ranks, all the way to the calm, cool, and collected silver and gold at the very bottom. Okay, so we've built this powerful list. It's a great achievement. But what's it actually good for? What can we do with it in the real world? Let's start with a huge industrial problem. Most of the metals we use aren't just lying around waiting for us. They're chemically locked up inside rocks called ores. So the big question is, how do we get them out? Well, guess what? The Reactivity series is our instruction manual. A metal's rank on this list tells us exactly how hard it's going to be to extract it. The higher it is on the list, the more reactive it is, the more it wants to stay locked up in its ore, and the tougher the method we need to force it out. And this slide spells it out perfectly. For the real heavy hitters at the top of the series, like potassium or aluminum, they're so reactive we have to use the most powerful method we've got, electrolysis. It's expensive, but it's the only thing strong enough. But for the metals in the middle, like zinc and iron, we can get away with a much simpler, cheaper method, just heating them with carbon. Okay, let's bring this all the way back home. Remember our poor, rusty iron gate from the beginning? Can our newfound knowledge of the reactivity series actually help us stop that from happening? Oh, you bet it can. And the solution is absolutely brilliant. It's called sacrificial protection. We know from our series that zinc is more reactive than iron. So what do? We coat the iron or steel with a layer of zinc. Now, when rust tries to form, the more reactive zinc steps in and corrodes instead of the iron. It literally sacrifices itself to protect the metal underneath. It's genius. Okay, let's put our new skills to the test. Time to think like a chemist. We've got a puzzle with 3 mystery metals, P, Q, and R. Let's look at the clues. First up, P and R react with acid, but Q doesn't. Okay, what does that tell us? Reaction means reactivity. No reaction means Q is our least reactive metal. Easy. Let's put Q at the bottom of our list. Now for clue 2. P's oxide can't be reduced by carbon, but R's oxide can. Remember our extraction methods? The harder it is to extract, the more reactive the metal. So if P is too tough for carbon, it must be more reactive than R. So P is more reactive than R. And we already know Q is the least reactive. There's our answer. The order is P, then R, then Q. See? We just solved it using the rules.
And this amazing map ties it all together. It shows how this one single, powerful idea, the reactivity series, is the key that unlocks everything else. It connects how metals react, why they displace each other, how we get them out of the ground, and even how we stop them from rusting away. It's all connected.
So in the end, the reactivity series is so much more than just a list to memorize for a test. It's a predictive tool. It gives you the rules of the game for this epic clash of the metals. So the real question to leave you with is, now that you know the rules, what other chemical battles can you predict? That's the real power you've gained today. Thanks for tuning in to The Explainer.